Okay, let me start the recording. Okay, Bismillahirrahmanirrahim. Okay, dear students, last time we were discussing the plate welder design, and I have just explained some differences of the plate welder as compared to the hot rolled beam section and what are the type of the plate welders. Okay, here I will give you the overview of the plate welder and its differences as compared to the ordinary hot rolled beam. So girder is a special type of beam, so that is custom made or tailor made. We make that beam. Let me share these slides again. So can you see these slides?
Yes, sir.
Let me start the recording again. So Bismillahirrahmanirrahim. So dear friend, I was explaining the difference of the plate girder as compared with the ordinary hot rolled beam section. So first of all, plate girder is a special type of the beam where the flanges are designed based upon maximum bending moment and the webs they are designed for shear forces. And then we can join both flange plates and the web plates by fastener or by welded type of connection. So as compared to the hot rod ordinary beam, which is molded in the factory after melting the steel. And also the hot rod beam section, they are used for the conventional building, but for special type of structure where we need to achieve the larger span, for example, for the bridges and also for heavy load. For example, you can see that on our canal. So we are having a plate girder bridges for the trains, for the train load, because even though the span is very less, but they are subjected to very heavy load. So if we are using the plate girder as a beam, so in that case, we can achieve larger economy. So plate girder usually consists of built-up section. So actually they are always built-up section because they are not hot rolled. So we are making the plate girder as per our requirement. The other thing that I have already explained in our beam design topic. So in our beam design topic, actually our hot roll section is compact based upon three criteria. For example, number one, web is continuously connected with the flange. So there is no any web local buckling. Web local buckling mean that web is compact with reference to web local buckling. So B over T ratio of the web, or I can say that lambda W value of the web is less than lambda P value as given by AISC. So also the flange local buckling is also avoided. So flanges they are also compact with reference to local buckling. So it means that the type of the beam section is only the function of lateral torsion buckling. And how we check that lateral torsion buckling? We compare the unbraced length with the plastic length and cylinder length, which is LP and LR respectively. So here I will show you the formula again that we have already used in beam design topic. So in case of our hot rolled beam design, so we always keep, for example, this formula. This is for lambda PF. Just like we are having the LP and LR value, in the same way we are having limiting slenderness ratio value for plastic buckling, inelastic buckling for the flange and elastic buckling, which are referred as lambda PF and lambda PR. So lambda PF for unstiffened element or for the flanges are 0.38 under root E over Fy, and for a 36 steel that is 10.8, that we always check in hot rod beam section. But in the same way, for angle section, lambda P value is this one, and for web. So this is the lambda P value for the web. So lambda P value for the web or lambda PW, you can say that that is 3.76 under root E over Fy. And for a 36 steel, this value become approximately 107. So what does it mean? In hot rolled beam section, lambda PW, which is height of the web over thickness of the web ratio, is always kept 107. So we make sure that our web is compact. If the lambda PW, height of the web over thickness of the web ratio, is more than 107, it means that our web will be non-compact. And we are having another limiting value for lambda r. For example, lambda r value for unstiffened rolled flanges is 1 time under root E over Fy, which is 28.4 for a 3060. For built-up section, lambda r value can be computed by this expression. But for the web, stiffened web purely in flexure, this is the lambda r value. Lambda r value means 5.7 under root E over Fy, which is 162. So if lambda w is more than lambda p, less than lambda p, so web will be compact, which is always satisfied in beam section, hot rod beam section. If lambda p is more than, lambda w is more than lambda p value for the web, which is, I have discussed, which is 107 for 836 steel, but less than lambda r value for the web, which is 162. So our web will be non-compact. It means that this web will be thin because height will be larger as compared to thickness. So this web will never fail due to yielding. It will fail due to the inelastic buckling. The inelastic buckling means that before failure, some of the web will be in the elastic range and some of the web will be in inelastic range. So the overall stress at failure will be less than Fy. But if height of the web over thickness of the web ratio is even more than lambda r, then this web will be cylinder. So what we are doing in case of hot rolled beam section, we always keep height of the web over thickness of the web ratio less than 107, less than this parameter. But in case of plate girder, we always use cylinder web. Cylinder web being very thin web. And how the web will be cylinder? Because we keep the height of the web over thickness of the web ratio more than this value 162. So what I can say, in ordinary beam, our web is always compact. But in case of plate girder, our web will always be cylinder or very thin. So why we want to make it thin? Because we want to save the material. Instead of providing the web of larger thickness, we can provide the web with minimum thickness, and later on we will check its shear capacity. If the shear capacity will be less, then we can increase the shear capacity by providing the stiffening plate. So here, for plate girder, height of the web over thickness of the web is always more than lambda RW value, which is 5.7 times under root E over Fy. And for a 36 steel, this value is approximately 162 or 161 point. So how this ratio will be more? Either we can increase the height or reduce the thickness to make height of the web over thickness ratio more than 160. So in plate girder, we always use web very thin as compared to the hot rolled beam section. Another thing, in plate girder, our flanges, they may be compact or non-compact, but they will never be cylinder. So It means that height of the web over thickness of the web ratio will always be more than 161.2. But AISC says that there must be some upper limit. So upper limit is, there are two formula. So height of the web over thickness of the web ratio should be less than zero point 0.4 times more than 1.5. What is A over H ratio? I will show you. So A is the spacing between the stiffeners and H is the height of the web. So if spacing between stiffener is more than 1.5 time of the H, it means that stiffener they are placed at larger place spacing. So in that case, the web will have the minimum shear capacity. So if in that case, AISC says that we have to restrict H over TW value less than 320. So height over thickness of the web ratio should be more than 161.2, but less than 320. Because if in this formula, if we are substituting Fy 250 megapascal and E value 200,000 megapascal, so we shall get this answer. And if A over H ratio is less than 1.5, means spacing of stiffener is less than 1.5 times of the height of the welder, then instead of using this formula, we shall limit the maximum value by this formula. Height of the web over thickness of the web should be less than this value instead of this. And if we are substituting the values for A3060, so we shall have the answer 339. But instead of using two separate equations, so actually this is a critical because we ignore this because both values are very close because this condition is more critical or more unsafe. So for our design, for a conservative design, even though spacing of stiffener is less than 1.5 time of the height of the web, we shall only use this condition. So height of the web over thickness of the web ratio should be less than 320, but it should always be more than 161. And how we can make sure, we shall discuss into this procedure. So girder, plate girder is always a non-compact or cylinder set. Why? It means that our plate girder may be non-compact based on even flange local buckling and web local buckling, and also based upon later torsion buckling. So in case of our hot rolled beam section, so our hot rolled beam section, it may be compact because it is compact based upon line local buckling and web local buckling. And also if unbraced length is less than LB, so our hot rolled section may be compact. But in case of the plate girder, it will never be a compact section because it is not satisfying all the four conditions. Number one, it is not thoroughly connected with the flange. Number two, our flanges may or may not be compact, but our web, it will always be a cylinder. And further, it may also be non-compact based upon later torsion buckling. Then the type of the plate girder. So first, depending upon the mode of connection, I have already shown welded or riveted. So I will show you the figures again. So these are the riveted or fastened type of the connection is used here. And these are the welded type of the plate girder where we are connecting the flange and the web plate by welding. Box girder. Normally this type of the girder, they are used for heavy load and wherever there is a chance of torsion in the plate girder. So normally in curved bridges, I will show you. So these are the box girder. So for the curved bridges, in case of the curved bridges, they may be subjected to twisting or torsion. In that case, we need to provide the box girder and they are not open. So this type of the configuration is used. For example, if we want to use a web of 10 millimeter thick. So instead of using one single web, we use two web plates, each 5 millimeter, but the combined thickness may be 10, and we are placing that web in form of two plates at the end. So in that case, the torsional resistance will be more, because if you know the formula for the torsion, the torsion stresses are equal to tau rho over J, torque multiplied by the radius and divided by polar moment of inertia. So torsion stresses, they are maximum at extreme fiber. For example, at along this periphery. If no material will be available, so no resistance will be available at periphery, so bridge will be subjected to twisting. But if we are providing the webs at edges, so the material available at edges, it can resist the twisting. So we can also use the three webs. So instead of having the I section, we can make the box section. So this will be a box plate welder. So at the end, we can provide the cover plate. Next is the hybrid. If we are using the flange of different steel and web of different strength of steel, then this type of the girder will be referred as a hybrid. We are using the same material but of different strength. So this is the hybrid. A composite bridge will be the one where we are using two different type of material. Maybe flanges may be made of, maybe you can say that steel, and the web it may be made of any other metal, maybe aluminum, just for example. So, or if the top flange is embedded in the concrete, so some portion of the concrete slab will also contribute to the flange strength. So in that case, that will be composite. Composite, if we are using two different materials. Hybrid, we are using the same material but of different strengths. Crane bridge. So crane bridge, we are having two type of the crane. For example, in our test floor lab, so we have to design a special type of the beam which is very heavy, just to lift or carry the load. So this crane bridge, it is a built-up section which is designed based upon the maximum load which we supposed to lift by this crane bridge. And also this crane bridge, actually it is moving on this runway bridge. So N type, in N type, along with vertical stiffener, we also provided diagonal stiffening plate. If applied shear force is very large, to increase the shear capacity, we provide the stiffener also in diagonal direction. So this type of the plate girder may be uh, called N girder. So it will behave just like maybe truss. So based upon shape, so we are having this convex bridge. You can see a larger depth in the center and a lower depth here. So why this depth is larger? Because the depth is optimized based upon maximum bending moment. So you can assume that this is a simply supported beam which is subjected to load UDL. So bending moment is maximum in the center. So an economical beam will be the one which is having this same shape as of its bending moment diagram. So I have already explained. So based upon the bending moment diagram, we have computed the various depths along length. So maximum bending moment is in the center. So we are having the maximum depth and minimum depth here. We always require some depth to satisfy shear capacity. And I have already explained this concept in my previous lecture in this slide. Because based upon bending moment, we can compute the depth at various cross sections along the length. So similarly, this is the convex, the concave. You can see that depth is lesser in the middle, but it is more at the edges. Why it is more? Because this is continuous plate girder. So you cannot see any discontinuity over here. So in case of the continuous plate girder, the continuous and they are considered as a fixed force. So you know that at fixed force, movement is larger as compared to the center span. For a continuous beam or fixed-handed beam subjected to UDL, movement in the center is omega L square by 24, and movement at the edge is omega L square by 12. So movement at the edges is twice as of in center. So it means that we need larger depth over here. So we are having two type of the bridges. Here you can see that the bridge deck is spotted at the bottom flange. And here you can see that the bridge deck is spotted on the top flange. So if the bridge deck is spotted on the top of the flange plates, then this is simply called plate girder bridge. And if the bridge deck is spotted at bottom flange, this will be referred as a through bridge, through plate girder bridge. Why through? Because traffic is passed. Okay. So I was explaining. So this type of the bridges you might have seen on our canal, across the canal at many places, maybe at Dharampura or maybe at any major crossing. And this is called Delta Bridge. And here you can see that the top line is braced with its own web by using a diagonal plates. So continuous bracing to the compression flange is provided by the diagonal plate which are welded or connected with its own web. So this is referred as a delta bridge. And this is a third bridge. Okay, here you will see that these are the typical plate girdle bridges which are do not have uniform shapes. So the cross section along the length is designed based upon shear force and bending moment diagram at that point, depending upon our requirement. So uniform depth is not provided just to save the material. And similarly, at this point, you can see that maybe a larger depth is required, maybe a larger bending moment is acting, and here a less bending moment is there, so a less depth is required. And in this case, maybe a less shear force is acting just to save the material. So holes are punched to make the structure lighter. Here you can see this is a typical crane bridge or crane girder, which is moving on runway rail. So this is a special type of the girder that we need to design depending upon the maximum load that we want to lift using this crane bridge. So pre-stressing, sometimes we provide the pre-stressing stand at the bottom just to produce the negative bending moment so that if a positive bending moment is acting due to applied load, so it can be countered. So delta girder I have also shown. So this point I have also explained. So varying cross section girder having more depth in region of greater movement may be economical in certain cases. So I have given you these examples. So plate girder as compared to the trusses. So fabrication cost is lower for trusses, but higher than for rolled beam section. Okay. Fabrication cost of the plate girder is less than trusses, but fabrication cost is more than as compared to the hot rolled beam. So fabrication cost or labor cost is more in truss because it involves too many connections. So at the each joint, we may have 3 to 5 members which are to be connected with the girder plate. We need to punch the hole or either we need to weld. So it means that a lot of labor cost is involved. But on the other hand, in case of the plate girder, so joining the flange with the web is rather easy as compared to the truss. So due to relatively stronger axis stiffness, vibration, and impacts are not serious problem for plate girder. So in case of the plate girder, we are having the material throughout the depth. So it is having higher stiffness also about y-axis. So they are not susceptible to vibration. But in case of the trusses, so trusses are having larger moment of inertia, maybe about x-axis, but in lateral direction. So they are having relatively lesser moment of inertia. So due to these some wind load, they or maybe some heavy load, the trusses may undergo some vibration. So plate girder requires smaller vertical clearance than trusses. So normally trusses are used when the span is very large or very heavy load is acting, because the trusses normally having larger depth, and we use this skeleton assembly just to reduce the metal. It means that if the depth will be larger, so we will have less clearance underneath in case of the uh, bridge on the rivers or on the canal. So plate cutter, they are having relatively lesser depth, so we will have larger clearance. Detailing for truss and construction according to these details, especially for connection, is quite involved as compared with the plate cutter. So more labor and more consultation is required while during detailing and constructing the connection or interests as compared with the plate cutter bridge. Yes, next, this is very important. So in case of the plate cutter, if any truck or any other vehicle, it strikes the plate cutter, so it can just produce the dent at the region of collision, so which will not cause any collapse or progressive failure. But if a bridge or any vehicle strikes and it break any one member of the truss, so breakage of one member, it will cause the collapse of the complete truss. Because if any one member is broken, so the truss may become unstable, because the triangular configuration will not be remain same. So if the triangular configuration is not maintained, so the truss will become unstable, so it will lead to the progressive failure. So any one member failure in truss can cause the failure of the whole truss. But in case of the plate cutter, if any collision occurs, so it can damage only the local part. So maintenance, including painting, is easier in plate cutter as compared with truss. In trusses, we need proper painting at the joints in the corner where we are having connection. But painting of the plate cutter is rather easy. Material cost for plate cutter is usually higher than as compared to the trusses. Actually, in trusses, we, for example, I will give you the example. So this is the end cutter. So actually, if I cut the material from this triangle region, from all triangle region, so it will become the truss. So this truss will have the approximately same capacity as compared to its equivalent plate cutter if we do not cut the material. So when we are cutting the material, it means that we are making it economical as compared to the material cost. But this material cost can be compensated with the labor cost, because we require more labor in constructing or detailing the connection in case of. Okay, next is very important topic that we are going to start, which is called proportioning of section or proportioning of plate girder. Sometimes we ask in the examination and the quiz, what do you understand by proportioning of plate girder? So proportioning of the plate girder is the selection of the size of the web and size of the flange, based upon our strength requirement. Strength requirement means that based upon applied bending moment and shear force. So selecting the appropriate size of the web and the flange which are satisfying our strength and other stability requirement is referred as proportioning of plate girder. So how we can do the proportioning of the plate girder? So there are certain guidelines. So whenever we are selecting the size of the flange, and the size of the web. So AISC has given one major condition. He says that area of the web divided by area of the flange, or web area to the flange area ratio should be more than 10. So AW is referred as area of web to the area of the flange ratio. So web area is always 10 times more than the area of the flange in plate girder. So section modulus must be sufficient to resist the applied bending moment at various sections of the girder. So the section must have sufficient stiffness or section modulus to resist all the bending moment along the length. So we shall use this condition. Web with or without the help of stiffener must provide adequate shear strength. So we may provide the stiffening plate or we may not provide the stiffening plate. But anyhow, in both cases, the shear strength of the web should be more than applied shear force. And how we will satisfy, we will see in our upcoming slide. So moment of inertia must be sufficient to keep the deflection within the limit. So flanges are designed for bending moment, web are designed for shear force, and we select the depth based upon also the deflection. So all the deflection must be within the allowable range. The moment of inertia is the measure or the main geometric property which we are using to control the deflection. Lateral bending stiffness of girder must be sufficient to prevent lateral torsion buckling. So lateral torsion buckling is also controlled by providing the lateral stiffness. Lateral stiffness means that you might remember, I will show you again in plate girder, we use RTS value, which is the radius of gyration of compression flange plus 1 by third of compression web. So this is the parameter actually which is controlling lateral torsional buckling. So it must have sufficient moment of inertia or radius of gyration about y-axis. Stability must be provided to non-compact web through the use of bearing and intermediate stiffness. So earlier I have told you that, maybe I will revise it again. In case of the plate girder, lambda W value is always more than lambda R. It means that our web, they are always cylinder. Cylinder means that the web will always fail due to buckling or elastic buckling. And this buckling will occur at a stress value less than Fy. So if our web is cylinder, then we make it stable or we increase its shear strength by providing the bearing stiffness and intermediate stiffness. The intermediate and bearing stiffness, they are the stiffening plate which increase the shear strength of web or increase the stability of the web against local buckling or web buckling. Then there is a procedure. So actually I need to change this procedure because stress rate should be in the top to avoid. So first of all, actually, we compute the self weight in case of the plate girder. And then we select the depth. So let me just reverse the slide. And now let me delete. So first of all, what we do, we assume the suitable self weight of the plate girder. So just to revise the or to compare it with the beam design. In beam design case, we assume the self weight by three parameters. Number one, if we are given dead load directly, then in that case we assume the self weight 10% of distributed dead load. And if dead load is not given, then we assume the self weight as a 5% of distributed live load. And if dead load, live load, they are not given directly and we are directly given the factored load, then we assume the self weight as a 3% of factored load. But this is different in case of plate girder. So in plate girder, we rather use an empirical formula. And this empirical formula is given over here. So this 0.67, you can say that this is 2 by 3. So when I copied from previous slide, so I could not copy this equation. So this 0.67, you can say that that is 2 by 3. So self weight is assumed as a 0.013 time of moment power 0.67 for 2 by 3. So what we do, first of all, we will plot the or determine the maximum bending moment in plate girder without self weight. And based upon maximum bending moment without self weight, we are computing MU, which is maximum bending moment, without including self weight. And then by using this formula, we can determine the approximate self weight. The approximate self weight is approximately 1.3% of the factored bending moment power 2 by 3 or 0.67. After computation of the self weight, we add this self weight to the dead load and we will compute the modified bending moment again. And this bending moment is including the self weight also. And then what we will do, we will compute the depth of the plate girder. So very first step is that after computing the self weight, we always select the web size first. The web size is calculated or decided, then we will compute the flank size. So a web or the height of the plate girder in order to control the deflection is always kept between L by 6 to L by 15. So L by 6 is the maximum depth and L by 15 is the minimum depth that we can use. But mostly for the economical consideration or practical consideration, so the depth is kept between normally L by 10 to L by 12. But for the economical consideration, we can use an empirical formula which is given here. So height of the web is computed 1.1 time of factored maximum factored bending moment including self weight power 1 by 3. So from here, whatever is the answer we are getting, so we need to use the depth in a multiple of 25 millimeters. Round the height or depth of the girder in a multiple of 25 millimeters. Maybe to upper side or lower side, whichever is the nearest one. But normally we round to the upper side because here we are getting just approximate depth, not the actual. So it means that you can round the depth of the plate girder to the multiple of 25 millimeter to the nearest side, but mostly we round to the upper side. So where mu is the maximum factored moment, so you can also write including self weight. In this equation, mu is in kilonewton per meter. So kilonewton per meter is equal to Newton per millimeter. But in this equation, movement should be in Newton and millimeter. So that's why that is how you may get the depth in millimeter. Okay, next is we will select the thickness of the web. So thickness of the web, first of all, we will see that what is the maximum thickness of the web that we may provide. That maximum thickness will not always be provided, but that parameter is computed to make sure that the depth of the plate gutter should always be less than this parameter. So I have already shown you that. So in case of the plate gutter, height of the web over thickness of the web ratio is more than lambda r value. So let me maybe modify this. So I lambda r w value. That we have already discussed. So this lambda RW value is 5.7 times 100 E over Fy. So for a 36 teeth, if we are using 250 megapascal, so if we substitute the E and Fy value, so this value is 161.2. So if we are comparing the height of the web over thickness of the web with this minimum limit, so corresponding to this minimum limit, we may have the maximum thickness of the web. So here, thickness of the web will be equal to height of the web divided by 161.2. Because if the height is divided by a lower value, we will have the maximum thickness. If height is divided by 320, that is the upper limit that we have already discussed, we will have minimum thickness. So we cannot provide the thickness of the web more than this value because we have already computed the h. Because if thickness of the web will be more than this parameter, then height of the web over thickness of the web ratio will be less than this parameter. So our web will not be cylinder, it will be rather non-compact. So this is condition will be used only to check that whether the thickness of the web is less than TW maximum. But anyhow, the thickness of the web is computed by three different expressions. We will compute TW1, TW2, and TW3 that you can see in upcoming sections. And we can provide the minimum thickness, which is maybe larger out of these three. So we are having TW maximum and TW minimum. And minimum value will be larger out of these three thicknesses. So these three thicknesses, how we can determine? Number one, TW1, that is based on corrosion resistance. So AISC says that if a plate girder is protected against corrosion or it is properly painted or sheltered, then minimum thickness of the web should be 6 millimeter in most of the codes or 8 millimeter. But if plate girder is not painted or protected against the corrosion, then thickness of the web should not be less than 10 millimeter. So we can assume that the plate girder is not painted or sheltered against corrosion. So we can assume TW1 depending upon corrosion resistance as 10 millimeter. Then TW2, this condition will be based upon the same guideline that we have already discussed. Because height of the web or thickness of the web should be more than this value, 161, but should be less than this value, 320. These two criteria. So again, TW2 is based upon this criteria. If web of the plate girder is two cylinder, very thin, so we are not going to make it very cylinder, very thin, because if it will be very thin, then the web may buckle at a very less stress value. So if it is buckling at very less stress value, So its shear capacity will be very small. Just to avoid this, we are having some upper limit for A over the height of the web over thickness of the web ratio, or some minimum limit for the thickness of the web. This behavior is different from the ordinary local plan buckling. So we have already considered the known two case. If A over H ratio is more than 1.5, so we can use this value, height of the web over thickness of the web ratio equal to 0.4 E over Fy, and for 250 megapascal steel, this ratio will be this expression will be equal to 320. And if A over H ratio is less than 1.5, then height of the web over thickness of the web ratio should be less than 339. So critical condition is this: if the spacing of the stiffener is very large. So if A is more than 1.5 H, in that case, even though we are providing the stiffener, we assume that we haven't provided stiffener, because if spacing of stiffener is very large, so web will be remain cylinder. So out of these two, the critical condition is this one, 320. So TW2 will be determined by equating the height of the web over thickness of the web ratio with 320. Second value is more critical and may be used in case, not second value, the first value. So here, so first value is more critical, which one? This one. So we are using H over TW ratio with 320. So here, because we have already determined the height, so thickness will be equal to H divided by 320. So TW2 is determined by H over 320. Then TW3 will be based upon shear strength. Okay, you are already familiar with this formula. To satisfy the shear strength, applied shear should be equated with the shear capacity of the web. Vu is equal to this capacity, and capacity can be determined by this formula. Phi V is 0.9. 0.6 is the factor to convert the normal strength into shear strength, multiplied by the area of the web, and CV value. That is the plate buckling coefficient. Okay, here CV value is 1 if web is fail in yielding, and we use this expression from here, not which is the I have already discussed 62.3. Yeah, this value. So if height of the web over thickness of the web ratio is less than this parameter, 2.24 under root E over Fy, which is 63.4, then our web will fail due to yielding. And in that case, CV value will be equal to 1. But in case of plate girder that we have designed, I told you that our web is always cylinder, because we are keeping the height of the web over thickness of the web ratio more than 161.2. It means that if our web is cylinder, then if our web is cylinder, so in that case, web will fail at a stress value less than yield value. So in that case, Fy value will not be equal to. So web will fail at a value less than Fy, which is critical stress. So in order to reduce the Fy value to F critical, we are using CV value. We are assuming that web will fail at a yield stress equal to 60% of Fy value. So in that case, we are assuming CV value as a 0.6. So because web will fail due to the local buckling, so it will not fail due to yield stress. So CV value is assumed as a 0.6. To provide the required shear strength, considering 60% of yield shear strength for cylinder web, so CV value is assumed as a 0.6. So here you will see that 1.6 is to convert the shear strength into normal, and other 0.6 to convert the yield strength into critical strength. So in this formula, we're supposed to use F critical against here. So you can say that if, okay, I will explain in the next topic, not here. So by equating this equation, we know the VU value and we know the Fy value, we know height of the web, we know CV value, so only unknown is thickness of web. And by equating this equation, we can separate out the thickness of the web. And if VU is in kilonewton, we can multiply with 1000 to convert into Newton. And we can substitute the value of 5V, CV value, which is 0.6, and Fy into H that we have already computed. So after substituting the value, you will have a more simplified formula for TW3, which is 12.4 into VU over H. So in this formula, VU is in kilonewton and height of the web is in millimeter. So in this way, you can compute TW3. So if you are computing this, so I will should rather also use this value as a CV, because CV value is the coefficient which is converting the yield strength to the critical buckling strength. So TW3 will be computed by this formula. So we have computed TW3, TW2 from this formula, and TW3 from this formula. The larger value out of TW1, TW2, and TW3 will be our adopted thickness of the web. And this thickness of the web should be less than this maximum. If this is more than TW maximum, so we shall use the TW maximum as our required. So web thickness close to the minimum is selected. So out of these three thickness, whichever is larger is selected as a thickness of the web, but is rounded to the higher whole number millimeter up to 10 mm. So if thickness of the web is less than 10 millimeter, then it is rounded to the upper integer value or upper whole number. If thickness of the web is 8.1, we shall select the thickness of the web as a 9 millimeter. If thickness of the web is 5.5, so we shall select 6 mm. But if thickness of the web is more than 10, then it is selected in this range. For example, if the thickness of the web is 12.1, so 12.5, we shall not select 13. Rather, we will select the next available size as a 15. If the thickness of the web is 16.8, then we shall select 18. So if the thickness of the web is less than 10 mm, then it is rounded to the whole number, next whole number value. But if it is more than 10 millimeter, then it is selected in terms of following available size on the upper side. Okay, next, after selecting the web area, Now we will decide the flange area and how it is selected. Just I'm going to show you this equation. We compare the applied bending moment with the moment carrying capacity, this concept. But what we do, we decrease the moment carrying capacity to 5 mm that I have already explained. This is basic design equation. So we compare the applied bending moment with the reduced moment carrying capacity, or with the design moment carrying capacity, and it is further multiplied with an RPG value. So what is this RPG value? RPG value is the moment capacity reduction factor for plate girder due to thin web. Why it is used, I will explain. First of all, assume that there is no any RPG, and moment carrying capacity is based upon compression flange, and it is equal to Fy compressive force in the flange. So I have already explained in this slide how to get this formula here. So if we know the compressive force in the flange and it is multiplied with the lever arm, which is maybe height from here to here. So maybe lever arm or H simple value. And this compressive force in the flange is equal to the stress, compressive stress in the flange into the area of the flange plate and multiply by lever arm. And these stresses, they can be computed by My over I or M over section modular. So this flange will fail when these stresses will be equal to yield stresses. So the rest of the formula is same. So lever arm is H value that I have used. So same formula. Compressive force is equal to the yield strength into area of the flange, and H is the lever arm. Okay, here it means that moment carrying capacity is based on area of the flange and into height of the girder or lever arm, or H by 2 you can say that. So actually, when, because we know that web is a cylinder, or we are using very thin web. So it means that when we are applying the load, so web buckling will occur before the flange will fail due to yielding. So when a web will buckle, so at buckling point, the depth of the plate girder will reduce because the flanges they will come closer to each other. Unlike here, the way there is no web local buckling, we will have the larger depth. So it means that when the web will buckle due to web, the height of the plate girder will be reduced. If height will be reduced, then moment carrying capacity will be reduced. So how much depth will be reduced? We are considering indirectly by introducing a factor RPG. So RPG value is the plate girder flexure strength reduction factor due to the unstiffened so cylinder web or thin web. Okay, what I want to explain that, so this height will be equal to d by 2 anyhow. So from just if you know this formula, in this formula if we are equating, we know mu is divided by 5b rpg fy and h value, and it means that only unknown will be area of the flange. So we shall have this expression. So forget about this expression at a moment. So it means that we are computing the area of the flange by equating this equation. So if you are computing the flange area just by this equation, so at this point, we have assumed that all movement is resisted by flange. But I told you that the web, they are also providing certain resistance. So, or they are also contributing to the flexure strength. So we assume that 1 by 6th of total web or 1 by 3rd of the compression web is also resisting. So just to economize, we can subtract area of the web divided by 6 from this value to economize or reduce the flange area. So area of the web divided by 6 is subtracted from this expression just to reduce the flange area. Why? Because here we are assuming that compression flange and 1 by 3rd of compression web. So I can, so this portion, this area is equal to ACW, compression web. So this is either equal to area of the compression web divided by 3. Because this web is in compression and this half web is in tension. So this portion is 1 by 3 of this compression web. So which is equal to total web area divided by 6. Total web area divided by 6. Why total web area? Because compression web is equal to half of total web. You see the screen? That
Yes, sir.
okay, I will be back. So before introduction, I was explaining that we can economize the flange area by assuming that 1 by 3rd of compression web is also resisting the bending moment, or total web divided by 6 portion we can subtract from our equation. So just to make this flange area economical, we have subtracted area of the web divided by 6. But if you want to use the conservative answer, so you can compute the answer by this expression. And RPG value, I have told you that that is the, so here actually this is equal to HC. Instead of using HC, you can directly use this H by 2, total H by 2. So for your understanding, so this HC value can be written also here. So you can consider that HC is equal to height of the web divided by 2. So RPG value is computed by this formula, and this value we can only compute if we are provided with the AW. And what is the AW? That is the area of the web over area of the flange. The area of the web we already know, but flange area we are supposed to compute. So if we know the flange area, we can compute the RPG value by this expression. So AW divided by 1200 plus 300 into AW into HC divided by thickness of web minus 5.7 100 E over F critical. It should be less than 1. So what is HC? Is the distance from the centroid to the nearest line of fastener at compression flange or inside face of the compression flange when welds are used. So I will explain this HC value. I will check, maybe I have written this expression. That was the option. Yes, in this slide. So HC is the distance from this center of this fastener to the center of the other fastener, or clear edge distance from this weld to the other weld. So this will be the HC. So while we are designing, I shall explain it again when we in our design phase. So at the start, we do not know RPG value because area of the flange is unknown. So what we can do, we can assume the RPG value as a 0.9 at the start. Just like we assume the U value shear lag factor or R value ratio of the net area to the gross area 0.85 in tension member design. Similarly, at the start, we can assume this value 0.9 and FCR as a yield strength 250. So 250 yield strength multiplied by 0.9. So combined answer will be 225. So for the simplification, we can assume this value as a 225 for our initial computation. So BFC is the width of the flange and TF is the thickness of the compression flange. Assuming that RPG into FCR combined value is 225, and after substituting this value over here, we can substitute 5V.9 strength reduction factor in bending and combined value of RPG into FCR as a 225. Then we can simplify this formula to this case. And in this formula, we need to substitute the moment in Newton and millimeter. So area of the web is already known. So we can determine the area of flange. After determining the area of the flange, actually, we need to check another condition. This is the area of the flange that we have just determined by this expression. If after determining this area of the flange, we compute this parameter, which is 387 minus 345 divided by CV value under root area of the flange required that we have just determined. And we compare this parameter with unbraced length of plate girder. If unbraced length of plate girder is less than this parameter, then this area of the flange that we have computed will be the final. No need to revise. But if unbraced length is more than this parameter, CP value we need to compute at the start, and area of the flange that we just have computed. If LB unbraced length is more, then we need to revise the area of the flange. And why we need to revise? Because we are assuming that later stiffness will not be sufficient. So we need larger flange area. So we shall revise the flange area by using this equation. So for so area of the flange will be revised by using this equation. So this area of the flange that we have determined previously by this equation. LB is then brace length for the beam. So whatever is this flange area, that will be the final. So after determining the flange area, we will determine the width of the flange and thickness of the flange. So I told you that flanges may be compact or non-compact. First of all, we will determine the flange dimension by equating the lambda f value with lambda p value. And this procedure I will explain over here. So we will equate lambda f equal to lambda p, and lambda f is equal to bf over 2 times of thickness of the flange for projected flange plate. If we multiply this side with the bf and also divide it with the bf value, so we will have the expression bf square divided by 2 times of the thickness of the flange into width of flange. So this is equal to the area of the flange that we have already determined. So 2 times of the area of the flange will go to the other side, and we supposed to determine the width of the flange, and we need to take the under root. So BF value will be equal to 2 times of the lambda p into the area of the flange required that we have just determined. So in this equation, if we substitute the area of the flange and lambda p value, and lambda p value for hot rolled or built up beam section is equal to 10.8483060. So this value lambda p for 83060 you can get from LRF design aid. So formula number 30 on page number 317. And this value we have already studied in our hot rolled beam section. So this value is 10.8483060. So unstiffened flanges of I-shaped rolled beam, channel, seas, and built up doubly for singly symmetric I section. So this means that this value is applicable both for hot rolled section and for built up section. So we don't need to consider lambda r. Lambda r value will be only used to make sure that lambda f is less than lambda r. So we are going to compute the BF value by this expression, and how to derive this expression I have mentioned. So after computing the BF value, we need to check that the BF value should be between h by 3 to h by 6. Because if the BF value will be more than h by 3, in that case, flange will be very large, but it will have the very less thickness. So it means that the flange will be susceptible for local buckling. But on the other hand, if the flange width will be less than h by 6, so in that case, even though we will have the larger thickness of the flange, but its lateral stiffness or moment of inertia about y-axis will be very less. So we always keep the BF value between h by 3 to h by 6. If BF is coming less than h by 6, so we fix the BF value equal to h by 6. And next is, I have just explained this. So BF value width of the flange is always rounded to the nearest multiple of 50 millimeter. For example, if you are having the BF value 540, so we will round into the multiple of 50 millimeter, and we can use this value as a 550. And if BF value will be 520, so you may select the BF value as a 500. So after that, because B of the BF value we have already computed, we know the area of the flange. If we divide the area of the flange by the BF value, we can compute the thickness of the flange. And later on, we can check the lambda f value by bf over 2tf value, and that should be less than lambda r. So if the thickness of the flange is less than 10, then we round the thickness of the flange in a multiple of 2 millimeters. And if the thickness of the flange is more than 10 and less than 40, we select the thickness of the flange in following order on the upper side. Let's suppose if the thickness of the flange is 7.9, we shall select 8 millimeters. And if the thickness of the flange is 8.3, so we will round to the multiple of 2 millimeter on the upper side, which will be 10 millimeters. And if the thickness of the flange is 13, so we will select the upper available size, which is 15. If it is 16, we compute it from here, then we shall select the size 18 millimeters. And if the thickness of the flange is more than 40, that you have computed from this expression, then it should be the multiple of 5 millimeters on upper side. For example, if the thickness is coming out to be 41, you shall select 45. If it is 53, you shall select 55. It should always be the multiple of 5 millimeter on the upper side. So I will stop here. So I suppose that I believe maybe from the next week you will have the on-campus classes. So the rest of the topic we shall cover in our on-campus classes. So if someone is having any question, he can ask me.
सर ऑन कैंपस तो आई थिंक 1-7 सेशन वाले आ रहे हैं.
नहीं आपने आना है.
सर हमने तो 22 को पहले तो हमें बोला हुआ था.
अच्छा एक मिनट है जो मुझे चेक करने दो.
मिड्स हमारे 22 को है, तो आई थिंक हमने मिड्स में ही आना है और उसके बाद फिर साइकोमोटर है मिड्स के बाद.
अच्छा चलो मैं चेक कर लेता हूँ फिर इसको ना, फिर मैं आपको बता देता हूँ. ठीक है.
ओके सर. सर बाकी डिजाइन क्लास तो हमारी खत्म है, सिर्फ अगर हुआ तो यही होगा थ्योरी के लेक्चर.
नहीं डिजाइन क्लास कितने का खत्म है अभी.
सर लास्ट लेक्चर में शायद आपने बोला नहीं
देनी है उसकी ट्रस्ट. नहीं वो मैंने बोल दिया था, मैंने कहा वो यानी कि डिजाइन फेज खत्म हो गया, लेकिन उसमें अभी आपको एक इंस्ट्रक्शंस देनी है.
ओके सर.
यानी कि ट्रस्ट शीट की ड्राइंग. ठीक है. तो रेज योर हैंड. All students who are present, please raise the hand. तो ये HB कौन है? हसीब है ये क्या? ये हर दफा ही नहीं होता. And who is this? हसन भट्ट. ये हैबिचुअल है. ठीक है. इसको नोट करो इस स्टूडेंट को. इसने फेल हो जाना, फिर इसने कहना कि मैंने इसको फेल कर दिया, ताकि खुद ही फेल हो जाएगा. इसने कुछ चाहता भी नहीं होगा. ये हैबिचुअल ही है. तो आपने नोट किया होगा, हर दफा यही होता है बंदा. तो इसी के एक्सक्यूज आ रहे होते हैं. चलो 1-2 दफा हो जाए बंदे के, 5 दफा हो जाए. चलो मेरे ख्याल में तो हमारे लेक्चर कुछ 30 में से तो 25 दफा ये है ही नहीं है. और इसको भी नोट करो सिया इन दोनों को. ठीक है. आज की डेट में.
ओके सर.
ओके इंशाल्लाह वी सी यू द नेक्स्ट टाइम.